Good morning. Today, I'd like to start looking at the idea of the flux of matter and energy across a surface. To get started, we're going to look only at the Newtonian case. We will pretend that we're back in the land of third semester calculus, and we're going to investigate a particular type of physical system which people call dust. We're going to have a collection of particles, all of which have equal mass, which I'll call little m, and all are at rest with respect to some inertial frame. We're going to have two things that we will call densities. Little n is the number density. It is the number of particles per cubic meter, or whatever units we're using. The particle density, even though these particles are at rest with respect to each other, can change from point to point. For instance, here the particle density is very low, but here it's bigger. We are also going to have the mass density. The mass density, rho, is the little n density, the number density, multiplied by the mass of each particle. So n is how many particles per cubic meter we have, while rho is the resulting number of kilograms per cubic meter that we have. I might think of the frame of reference in which the particles are at rest as being O bar, as we have many times in the past. If O bar is moving to the right relative to a frame O with speed v, then the Newtonian velocity is just the speed times what we called the I vector back in third semester calculus. The first thing that I want to investigate is this: how much mass per unit time is going to flow across a surface of a certain description that I'll give in a moment. As measured by O, the particles are moving to the right. I'm going to think about how much mass cuts across a surface where the x-coordinate is a constant. This will be relatively easy to figure out because the right angle direction to this plane, x equal constant, is parallel to the direction that the particles are traveling in. I'm going to think about a small amount of area in the surface that we're thinking about. It'll be delta y in the y direction and delta z in the z direction. I'm going to think about the amount of volume that passes through that square or rectangle in an amount of time delta t. The particles are moving with speed v, so the distance they travel in an amount of time delta t will just be v times delta t. The volume of this indicated rectangular box is the speed times delta t times the amount of area that I'm looking at in the surface under consideration. The number of particles that pass through the indicated rectangle of the surface is the number density times the speed times delta t times delta y times delta z. Each particle, though, has an amount of mass, m, so I can tell you how much mass passes through the indicated rectangle as well. The amount of mass that passes through the indicated surface in the indicated area in the indicated time is the mass of each particle times the number density times the speed delta t delta y delta z. Naturally, that tells me that the amount of mass that flows through the indicated region is just going to be the mass density times the speed times delta t times the amount of area. So if I divide by delta t, which represents the amount of time that's passed in this situation, and also divide by delta y delta z, which is the area in the surface, I find out that the amount of mass per unit area per unit time that passes through the surface is the mass density times the speed. We're going to call the amount of mass per unit area per unit time by a fancy name. It is the flux of mass across the surface that we're talking about, which in this case is a surface where the x-coordinate is constant. It's worth mentioning, though, that to calculate this flux, I have to tell you the mass density and I have to tell you the speed completely separate from each other. I could make the mass more or less dense without changing the speed. I could change the speed without making rho bigger or smaller. So logically, there are two completely independent things running around in this. When we get to the relativity part, that will go away. When we say that a particle crosses a surface, we mean that literally. It goes from being on one side of the surface to the other one. If I think about this same physical situation and ask what the flux of mass across surfaces of constant z-coordinate are, then the answer is 0, because none of the particles go from one side to the other. The flux of mass across surfaces of y equal constant will be 0 as well. That's harder to draw, so I'll just make the statement. What if the path of the particles doesn't cut across the plane at right angles? So in this case, I'm going to draw it so that I'm looking at the plane as seen edge on. This is the normal vector to the plane. I'm going to have to make some comments about that word "the" in a minute. This is the velocity vector of the individual particles. I need to figure some things out. Firstly, in amount of time delta t, how far do these particles travel? Now, in the direction of travel, they go a distance of the speed times delta t, of course. If I want to know the volume of this shape, I need to take the area in the plane and multiply it by the perpendicular height here. So I need to know this perpendicular height. The angle between what appears to be horizontal in this picture, the angle between the n vector and the v vector, is what I'm going to call theta here. I'd like to express this perpendicular distance in terms of theta. But remembering my trigonometry, it's not very difficult to figure out that the volume is the speed times delta t times cosine theta times the little bit of area that corresponds to the piece of the plane that I'm looking at. The number of particles in the box is obtained by taking the volume and multiplying by the number density. The mass in the box that passes through the indicated chunk of surface in time delta t is the mass of each particle times the number density times the speed dt cosine theta times the amount of area. So the mass that crosses the surface per unit time per unit area is the mass density times the speed times cosine theta, where theta is the angle between the ordinary Newtonian velocity vector and the ordinary Calc 3 normal vector. This agrees with our previous work. If theta is 0, you get mass density times speed, and if theta is pi over 2, you get 0. But wait, there's more to it than this. If you give me a plane, I'll have a normal vector for it, but I could multiply that normal vector by 2 and still have a normal vector. I could take this normal vector, multiply it by 1/2, and I would still have 1. It doesn't hurt anything to assume that I've normalized the right angle vector so that it has length 1. That will remove a lot of this ambiguity, but not all of it, because if a vector is at right angles to a plane, its negative is also at right angles. So there's still a little bit of wiggle room here. This is not going to be terribly important to us until the direction in which we're crossing the surface is important to us. We'll put that off for now. I'll assume that I've selected one of these normal vectors with length equal to 1. If I do that, then my flux of mass, which is mass density times speed times cosine theta, remembering theta is the angle between the v vector and the n vector, I can rewrite this as mass density times the speed, which is the magnitude of the v vector, times the magnitude of the n vector, which we've rigged up to be 1, times the cosine of the angle between v and n. That is to say, mass density multiplied by the dot product of the velocity vector with this unit normal vector. If I tell you the mass density, if I tell you the velocity vector, and I specify a plane, by which I will specify the normal vector, I can now easily calculate the flow of mass per unit area per unit time across that surface, the flux of the mass. Not to insult anyone's intelligence, but how much mass per unit area per unit time flows across the surface x plus 2y plus 3z equals 0 if the velocity vector of the particles are I plus j plus 2k and the mass density is 6. If you remember from Calc 3, the normal vector, a normal vector for the plane, is given by the coefficients of the x, the y, and the z. So vector I plus 2j plus 3k points at right angles to the plane. To make it have length 1, I'll divide by its magnitude. The velocity vector was given. The dot product of n and v is straightforward to calculate. Mass density times that dot product gives me the number of kilograms per second per square meter that crosses the surface in this situation. When we move to more general situations, even if I have a curved surface, at a given point to it, I can find the tangent plane and find a right angle direction to that tangent plane. In Calculus 3, we learned that you can do that by expressing the surface as g of x, y, and z equal a constant, and then a right angle vector will be the gradient of g evaluated at the spot you're interested in. We now have a really, really big problem because we have done a lot of thinking and studying on the matter. The gradient of g is not a vector in the sense that we usually think of vectors. It's a one form. If I say I want to take a vector and dot product it with a one form, that doesn't even make sense. Unless you're in Cartesian coordinates, when you convert components of vectors and one forms into each other, Cartesian and only Cartesian gives the same numbers for the components of the vector versus one form. So I could turn this into the vector version of gradient of g. In Cartesian, the numbers would be the same and everything will be fine. When we can't use Cartesian coordinates, that isn't going to work. And we can't use Cartesian coordinates if our space-time is curved. Another issue, mass density, according to who? Volumes are frame dependent. There's the Lorentz contraction. So we're going to have to specify in some reasonable way who it is exactly that's going to be measuring this mass density. As far as the time goes, time could be measured by a wide variety of individuals. We'll have to think really hard about the decision about whose time we're going to use. It'll turn out that the choice we make for this will be different from the choice we make for that. And I want my results, I want all the quantities that we're interested in calculating to be frame invariant. That means I have to write the quantity that I'm trying to get as a tensor quantity. A 0, 0 tensor would be a frame invariant scalar quantity, or maybe it's a vector, or maybe it's something else. But however we write it, it has to be frame invariant, or it won't have any real physical meaning to us. In the next video, we're going to begin exploring how we can deal with these issues. Until then, I hope everyone's having a good day, and I'll talk to you again soon.